All right, let's get started. Let's do this. So I found out why my slides weren't updated from the last lecture. It's because I didn't push them. I mean, if you don't push things to the repo, they don't show up. So we got this time. Oh, let me break my example first, too. Wrong ID. And my example broken in the wrong way last time. And that should be updated here. Oh, come on. Here we go. Okay, so we're updated. There we go. Oh, and these slides aren't supposed to be here. Those don't exist. Okay, anyway, let's get started. So today we want to get back into it and talk about WebSockets. Homework 4 for WebSockets is released. Project Part 2 released. We just had the Project Part 1 deadline this morning. It was due at 9 a.m. Now you have your repos. There's no actual submission or anything for this. And you have your repos, and you likely want to get started on Part 2, at least start thinking about that. You're free to continue pushing to your repos, updating your code and everything for Part 2. For grading of Part 1, what the TAs will do is go to your repo, and if there are commits after the deadline, they'll take your latest commit before the deadline, check out that version of your repo, and then grade based on that. So don't hesitate. If you want to get started right away on Part 2, keep committing, keep pushing. We're going to handle the grading that way. It's the best way to handle it. It's the fail-safe way to do it. Part 3 is also released. So if you want to look ahead and see everything that we're doing with the project moving forward, we have all that. All that is out. The presentation's been out for a long time. You can sign up for presentation times as well. That's been out. I see a lot of you have been signing up. Any other announcement that I have to make? Oh, we have, since Nicholas is here, Nicholas added this wonderful feature to the website, jump to current week. And it works so nice. I love it. I'm already addicted to it. We need it on 116 now, too. I already miss it on 116, it not being there. I swear there was another announcement I was going to make, but I'm blanking on what it is. Homework 5 should be released soon. The TAs have some ideas for Homework 5. I want to hear them out. We have a meeting tomorrow. I want to hear them out on their ideas before I release it, but Homework 5 should be released pretty soon as well. I want to get everything out there so you know what's coming up for the rest of the semester. What else was I going to say? There was something. Oh, the Project Part 2. Project Part 2 deadline is the morning of the start of presentations. For presentations, your project has to be deployed, and Objective 3 on Part 2 is deploying your project. I set this up in a way so it's fair to everyone. No matter when your presentation time is, you're expected to have you have to be deployed before your presentation. How do I word this? You have to be deployed before your presentation, and that's due at Part 2. So everybody has to be deployed at the end of Part 2 to make it as fair as possible. So if you have the last presentation time, it's not like you have more time to deploy. And some people are deploying right after the Part 2 deadline. Some people are deploying or presenting right after the Part 3 deadline. For the presentation, you don't have to have all your features implemented. I would, I expect most teams to have parts 1 and 2 features implemented. But even if you don't have all of Part 2 done, if you just couldn't get WebSockets working on your app for whatever reason, you can still get full credit on your presentation as long as all the features that you have implemented are functional. You can get max credit on the presentation. So there's no grading difference between having the first or last presentation. You present whatever you have. the last presentation, I would expect you to have parts 1, 2, and 3 done if you're presenting on this day. But even if you're presenting on this day and you don't even have all of part 2 done and none of part 3, like just demo what you have, do your presentation with what you have, and we'll still load test while I'll use your app during the presentation. And as long as it holds up and it works, whatever is implemented does function properly during that, you can still max out your presentation score. So just logistical notes on how all that works, especially if that factors into your decision of when to present. People always backload it. The last ones load up first. Wait, is that true in 3.12? But personally, I would take some of the first ones. I want to get it over with. But that's up to you and your team. Please sign up for a time, though, if you have any timing restrictions. Every semester, like, presentations start, and then somebody's like, there's only 1 day left of presentation times, and I can't make those times, so what do? I don't know. You should have signed up months ago. Figure that stuff out sooner rather than later. Like, if there is an actual legitimate timing issue and you let me know, like, today, I'll work with you on it. But when students, entire teams had no idea and didn't even think about it until presentations start, that one's frustrating. We should, when is the deadline for, right here, April 15th, last time to sign up for a presentation time. So April 15th, I'll finalize the presentation schedule. I did remember one more logistical note. Where is it? This day is going to get wiped off the face of the earth, as you already know. April 8th, I didn't update the schedule yet, but what I'll likely do is just push everything back a lecture and get rid of extra topic. This was open-ended. I didn't know what I was going to put here, so due to circumstances, I'll just not put anything there. Is probably going to be the answer. Okay. Any questions on any logistical notes? Where we're at in the course and what's going on? Do we need to give the TA the link to a repo? We'll use the one that you used when you created your team, the team formation form. That's the repo we have on record. If that's not the repo you're using, or if you were one of the random teams and never filled out that form, send me an email with your repo link and let me know what it is. I'll update my records. If you are one of the random teams, send me your team name too. I'll send out emails probably tonight. Anyone who hasn't, any random teams who haven't sent that information to me, I'll reach out and ask for that information because we obviously need that information. Who do I ask about whether or not a member of our team disappeared? You'll know more than I do. Have they been showing up to your team meetings? If you're not hearing from them, they disappeared. They're gone. We had the homework 1 final deadline. There's a decent amount of the class that's where their ride ended. So if somebody's disappeared, you can pretty safely assume that they're done with the course this semester. But I don't have the definitive answer because there are some students who got through homework 1 and since then decided to give up. I'm not going to notice that until the homework 2 final deadline. So there are some students who gave up before, haven't resigned, haven't officially failed yet, but have given up on the class. That always happens. So you're going to know more than I do if they gave up. We just had a project deadline. If you haven't heard from them and the deadline passed, like they're not helping you out. They're not part of the team anymore. Fill out the meeting report forms. Let me know that they were a no-show. They'll get 0 AOs, and you'll likely get a boost to your AOs. If your team didn't max out with 3 AOs for part 1 and you lost a teammate, likely when I do individual, it'll be a case-by-case basis, but when I do the individual grade adjustments, you're probably going to get a grade boost. And even without completing all the objectives, you might still get full credit. You work with, if you lose a member, you work with 1 less member, but there's enough teams that got pretty ravaged that after part 1, I'll see what the full situation is. Once I get the full picture, There's the potential of combining some groups. I know at least one group is a team of 2 right now. So if I have like a team of 2 and a couple teams of 1 or something, if that's the situation, I'm going to reach out to y'all and be like, hey, would you like to be a team of 4? I'll leave this decision up to all the students involved, but I'll give that option out there. We have that potential. All right, enough logistics. Let's get on with it. WebSockets. Let's talk about them. So the problem that we're facing is that we want real-time communication. That's the ultimate problem that we want to solve, just to set the stage for what WebSockets are going to do for us. We want real-time communication, which, I mean, we kind of have. If the user wants to send us information, they send us an HTTP response. As soon as they take an action, some AJAX is going to fire off that response. So it's going to fire off that request, and we get that information right away. What happens when we have information on the server that we want to send to the user, though? HTTP is a request-response protocol, meaning we get a request, we respond with a response. We have no mechanism with what we've talked about so far. Obviously, WebSockets is going to do this. That's what I'm building up to. But we have no mechanism so far for the server to just send information to the user. We can't do that, especially not in real time. The closest we got right now is AJAX and polling, where we have the client send us a request every second or so, or every few seconds, or every 5 seconds, every half a second, whatever your polling interval makes sense for your application. We just send requests every so often, and then if we have information to respond with, we respond with that information. We have new information. But our server has to wait for the next polling request to be able to send that information. This is a problem we can solve with long polling. That's something I mentioned in the class, but we never implemented long polling. We can solve it with long polling. It's kind of it's kind of an archaic solution. It's cumbersome. It's bloated. It's got complexity. It also has some advantages over WebSockets, to be fair, but just not one that we're going to get really into the details in this course. So what we want to do is get rid of this must wait for pull request. And for some applications, this isn't bad. For our chat app, this isn't terrible. We have polling set to 1 second, and sometimes other users have to wait up to a full second to see the new chat messages. It's not that big of a deal. But there are going to be applications where that is unacceptable, completely unacceptable. For example, if you're coding a game, maybe it's a first-person shooter where you need twitch controls and quick reactions, and you're waiting a full second to see what the other player did, that is completely unplayable. You can't do that. You can play with the polling interval, maybe put it down to like half a second, quarter of a second, maybe get that a little smoothed out, but it's just not the appropriate thing to send all these HTTP requests with all that extra network traffic. Also with polling, if there's no new information, say you have chat open and there's no activity, just everybody's idle at the time, and you're still firing off a request every second, there's a lot of just wasted network traffic to the point where, and it adds up fast, to the point where you can have issues with that. I had an issue with a chat app I put up during lecture, and everybody, puts up their stupid messages, and it's funny, which is part of why I don't do it anymore. I got sick of all the jokes, it's always the same messages that go up every time. But I did that one time with an app that used polling every 1 second, and I was estimating like 50 students, I think, were using the app. I think there were like 100, 150, 120, I forget how many in the room. And I estimated like 50 of them actually opened the app and were using it. And it was polling at 1 second. So if I have 50 students polling every second, that's, I keep making myself do math during lecture, 3,000 requests per minute. And then if they leave it open for an hour-long lecture, that's 36,000 requests over that hour. That's a lot of network traffic being sent just for people sitting there, not even using the app. Like they posted a few funny messages, and then they mostly just sit there, the tab's sitting in the background, and they forgot about it. And it was so many requests that DigitalOcean started blocking UB's IP address and sent me an email and said, hey, we just detected a DDoS attack. UB is attacking you, but don't worry, I got your back. We blocked that IP. So during lecture, the app didn't work anymore. And then I'm like, oh, crap, I got a bug. No, it's because DigitalOcean detected a DDoS attack. And it was just bad all around. So there are issues with polling, needless to say. So we want to do something better, something smarter. Something cleaner, more elegant, I guess. In WebSockets, I really do mean that. WebSockets is a nice, clean, elegant solution to this problem. We'll see more of the nitty-gritty details on Wednesday, where I'll go off and really sell it. Like, oh my goodness, look at how little overhead there is. There's significantly, almost no overhead to WebSocket communication. A really, really clean solution. So anyway, what are WebSockets? This is going to give us the full two-way communication. So the big advantage that we get here is that our server can just send information to the client at any given time. So with our chat app example, a user sends a chat message, we get that chat message, and immediately broadcast it to all users. We have network delay, and that's it. 100 milliseconds max, depending on the network location, everybody's physical location on the planet. It's going to be up to a couple 100 milliseconds delay if they're on opposite ends of the planet. Not much delay. So we can have this real-time communication, and that's what we're after. That's what we want. Real-time communication that involves server pushes, where server has to send data unprompted, so no HTTP requests. Because before, we have to sit there and wait for an HTTP request that we can respond to. With WebSockets, we're not going to have to wait for a request. We just send the message over the WebSocket. So this is what we want. This gets us all the solutions we want. Again, long polling does kind of solve the same problems. It gets us the same thing, albeit with a lot more overhead and extra complexity. WebSockets has so little overhead. It's really nice. And what WebSockets are can be summed up in just this line. WebSockets, what makes them just such a clean answer is they just leave the TCP socket open. What WebSockets are, well, let me build up to this by what HTTP is. What HTTP is we establish a TCP connection. We have a three-way handshake. We establish a TCP connection. The client sends us an HTTP request over that connection, and we respond with an HTTP response. And then we close the connection. We're done with that connection, at least in this course. And I mentioned the keep alive header before. We can keep the connection open for another request response. But in this course, we've just been closing the connection after one request response. What WebSockets does is, let's get rid of this request response thing. Let's get rid of this HTTP thing. Let's get rid of the HTTP headers. Let's get rid of /r/n. Let's get rid of request lines and status codes, all of that. Throw it all away and just use frickin' TCP for its intended purpose. TCP is already full duplex communication. It's a connection that we call receive and we call send all to receive and send, and we just do it, receive once and send all once. But we can keep calling receive. We do that with buffering now. We can keep calling send all. WebSocket says, let's forget all this HTTP stuff and just use TCP. We already had a beautiful protocol that does full duplex communication. Let's just use that. So WebSockets are mostly just TCP with minimal overhead that, again, we'll talk about Wednesday. So for the WebSocket connection, establish a TCP connection. And then normally it's one request, one HTTP request, one HTTP response, then we throw the connection away. What the protocol is going to do is the client is going to send an HTTP request that's going to be a different request than what we've seen before. It'll still follow the same structure and everything, but it will be an upgrade request. The client's going to say, hey, server, we just did this TCP, this three-way handshake and everything with the SYNs and the ACKs and all that stuff. We did that, and we established this connection on these ports and everything. It'd be really cool if we could upgrade this connection to a WebSocket connection. Let's just use this TCP connection as a WebSocket connection. Your server is going to respond with, sure, let's do that. And then client and server have agreed to keep that TCP connection open and use that for WebSocket communication. And we're going to send messages in the form of frames We're going to send WebSocket frames back and forth in a fully duplex way. The client might send us 100 frames without us sending any. We might send 100 frames without them sending anything. Or we might send 100 both directions. It doesn't matter. We're going to send messages back and forth without following any request-response protocol. We're just going to send information to each other at will. So that's the idea. We're just going to keep that TCP socket open and send WebSocket frames, which for now we can think of as just messages. We're going to send messages over that TCP connection. That's it. That's what we're doing. So we need to go through a handshake. I guess it's in the title. We need to go through a handshake to agree on this. Very similar problem to the TCP handshake. We need to solve the same problems. And specifically, we want to make sure that client and server both speak WebSockets. With TCP, with the SYN packet and the ACK packet, where we generate a random number, send that number, then add 1 to it and send it back. It's just some arbitrary thing that we do. But that thing is going to give us the security to know, not really security, but the assurance that we're both speaking the right protocol. We're both speaking the same protocol. So WebSocket, same thing. We need to verify that we're both speaking the right protocol. So we have a very, we'll see when we get to that slide, but we have a very strange handshake that's going to guarantee that we both speak WebSockets and also bust caching. We'll talk about it in a second. We don't have to modify our current request parsing functions, right? If we switch from TCP to WebSockets. It depends how everything's set up. It depends exactly what you mean. But I think I have an answer for you. Let me know if this isn't what you're asking. If you're using the router, you're using the whole setup that we've been building in Objective 1 for each homework. For WebSockets, your function that you give to your router, that is going to handle your WebSocket frames. So when you receive a WebSocket frame, you're not sending it to your request constructor. That's going to be handled inside that function after it's already routed to your WebSocket function. And I do recommend some modifications to that. You have to do something a little different. What I recommend is to modify your handle method. It's a method. Your handle request method. There we go. I got the words in the right order there. Your handle request method. Add a second parameter to that takes a reference to your handler. So inside that function, you can call receive and send all. And then you can, inside that function, go in your WebSocket loop. I'll give examples in code if this isn't making complete sense. It probably shouldn't yet. Inside that function, you'll handle your WebSocket frames. Let me get through the slides so I can get to that example. Okay, and here's part of how the handshake works. This is the simpler part of the handshake. The next slide we'll get into the rest of the details. Is the client is going to send us an HTTP GET request on our WebSocket path. The WebSocket path is defined by whatever it is in the front end. I think I have /WebSocket in the handout code, whatever it is in the handout, and it says it in the homework document as well. That answers my question. Thanks. All right. If you keep a TCP connection open, is it vulnerable to attacks? For example, can you give examples where man-in-the-middle attack might occur? Maybe. Not off the top of my head. Yeah, not at the top of my head. Not a quick answer anyway. We will address man-in-the-middle attacks when we get to HTTPS with TLS. We will get into that in certificates. We'll talk about certificates and all that stuff. And at that point, we'll prevent it by encrypting our traffic and having a key exchange and certificates and all certificate authorities, all these good things. We'll prevent it at that point. At this point, at this point, we're pretty much screwed to any man-in-the-middle attacks or any even eavesdropper attacks because our auth tokens are being sent unencrypted over the network. So we're completely vulnerable to pretty much every attack. Anybody using Wireshark is going to be able to steal your auth tokens because we haven't talked about encryption yet. We will solve that in Homework 5 content when we start encrypting things. But right now, we're 100% vulnerable to that attack. All right, so our WebSocket Handshake, we're going to get an HTTP GET request that's going to contain these 3 headers: connection upgrade with a capital U, upgrade WebSocket with a lowercase w and s. That's not a typo. That's what the RFC says, that WebSocket is lowercase. I don't know why, but I'm sure there's a good reason somewhere. And this sec WebSocket key with some random value, some random key. And that's the one we'll talk about, the key and accept, on the next slide. We're going to respond with a 101 switching protocols response code. So this is the first and only 100 level response code that we'll see this semester, the 101 switching protocols response. That's saying, okay, let's leave this TCP connection open, but let's switch the protocol, and we're going to switch it to WebSockets through these headers. We're going to duplicate the same 2 headers here, connection upgrade, upgrade WebSocket, match the capitalization, make sure your capitalization's exact. I don't know how forgiving or unforgiving browsers are about the capitalization, but just get your capitalization right and you won't have to think about it. I don't think about it because, I don't know, I just get the capitalization right. And the sec WebSocket accept with some accept response. So these headers, 101 switching protocols, and the key and response we'll talk about in the next slide, but let's talk about all the logistics, all the rest of the logistics first. You're going to get a request on your WebSocket path. You're going to specify that in the front end, or it's already specified in the handout code, what path this request is going to be given on, is going to be sent on. So if you get a GET request on that path, I'm going to be okay if you just assume that that's a WebSocket upgrade request. So if you're not checking these 2 headers, if you don't know where in your code you have if connection equals upgrade, if upgrade equals website, if you don't have that, I don't care. I don't even do that in my solution, to be honest. But you do have to read this WebSocket key, and then when you send your response, hard code your 101 switching protocols in these 2 headers. Just make sure these 2 headers are there, and then this header name, and then what you're computing is this value. So the structure, this is stuff we've been doing all semester. We're messing with headers, response codes, HTTP requests and responses and everything. Checking the method and the path to have some specific functionality. Nothing new here. It's the random key and the response that we really have to talk about. This stuff you just have to do, but you know how to do all this if you made it this far. And here's where things get a little silly. So let's figure out what this accept value is. So the sec WebSocket key header, the browser is going to generate a random value for this header, and it's going to be a different value for every single connection. There's no, like on Firefox, it's always going to be this value. There's nothing like that. Every single time a WebSocket connection is established, each browser, for each connection, it's always going to be a newly generated, fresh, random value for the key. So we get some random value that we'll have to read from this header as a string, and we're going to append this thing to the end of it. This exact string, this globally unique ID, is going to be appended to the end of whatever they give us as that key. And then we're going to take the SHA-1 hash of that, and then base64 encode that, and that's the value that we send in our sec WebSocket accept header. This value, should be hard-coded somewhere in your code. It can be a variable or a constant or something, but this exact string must be in your code somewhere. This exact string, this is in the RFC, like this specific string is in the RFC and says this is the one that we all use. So it's defined in the protocol to be this exact ID, this exact GUI. So this exact string, this isn't like an example or a sample. This is part of the protocol, exactly like 258 EA, FA, etc. is part of the protocol. The SHA-1 hash, we've talked about hashing. SHA-1 is just a different hash function. It's the predecessor to like SHA-256 or any other SHAs. And then base64 encode, I think I mentioned this in passing one time, but I'll give it a little more attention right now, is base64 encoding is a way to encode any arbitrary bytes as an ASCII safe string. This is a problem that we faced quite often in the course, mostly with images. I say never interpret your image as a string. There actually is another option to that, to solve that problem. It's a terrible option. You shouldn't do it. But you can base64 encode your image, which converts any arbitrary bytes into an ASCII safe string, an ASCII string. So you could base64 your entire image or an entire video into ASCII using a base64 encoding. Don't do that, but that's what we're going to do here. Don't do that for your multimedia. But we're doing that here because SHA-1 is going to spit out bytes. It's going to give us bytes, and then we're going to base64 encode those bytes because we have to set it to an HTTP header. Headers are ASCII only, so we need these bytes to be ASCII. So we don't have any other choice. We have to use base64 and encode this stuff, or else we can't use that in a header, use that value in a header. The reason it's a bad idea to use this with your multimedia, a few different reasons for that. One, it's going to inflate the size of all your files. Base64 can, I want to say triples, but I feel like that's an exaggeration. But how much? 50%. So 50%, thank you. 50% larger. So if you have a 1 megabyte file, or well, let's crank it up. 1 gigabyte file, now that's going to take a gigabyte and a half. In your entire file system, you might have a terabyte of images. That's a terabyte and a half now. That's going to add up. That's just completely wasted space because you're base64 encoding your bytes instead of just handling binary. Like, we should be able to handle binary as computer scientists and software engineers. And the extra computational power. So it's space inefficient, and it's also processor inefficient because every time you have to handle those files, you have to encode and decode using base64. It's going to take a lot more CPU just to handle that data when you should just be reading bytes from disk and sending them. Now you have to read a string from disk, base64 decode it, and then send it over the string, over the internet. So if you're ever tempted to base64 your just large binary files, please don't. Even though it's a solution, it is a terrible solution. Don't do it. Don't do it. I mean, maybe there's some specific use case where that makes sense, but probably not. Here we have to use it because we have to put bytes in a header, so that is the appropriate answer to this problem. Okay, so why do we do all this? This is a silly thing to do. One of them I mentioned already. You're never going to generate this except on accident. A browser who says, I would like to establish a WebSocket connection with this server, the server who responds with the correct accept value had to have followed this protocol, had to actually follow the WebSocket protocol. There is code on that server that's understanding WebSockets, and the browser says, okay, I am talking to a server that does understand WebSockets properly because they got this exact value following this really strange way of doing things. So therefore, we have a WebSocket connection because nobody's just going to accidentally generate the correct accept. It's just not going to happen. With this specific string and SHA and base64, never going to happen. You're never just going to get that value on accident on the right header. You know that they're actually speaking WebSockets. And then the second one is avoid caching. So we have a GET request on a specific path, and this GET request is going to contain a random value. This is the reason why the key is random every single time, and we're not just like responding with the GUI, because that would be enough to know that we speak the protocol. Just respond with this very exact specific string, and okay, we got you. We're on the same page. We're on the same RFC. That would do the first bullet point. But we want to avoid caching. That's why the key is random every single time. If the key is not random, we might have some component of our web app, something in between our server code and the client, usually a reverse proxy or a load balancer, something sitting there in between us and our client. That's installed by us. That's some third-party software. It's usually Nginx in my cases anyway. We'll put Nginx in between, and whatever we put in between there might have some aggressive caching settings, and it might say, okay, I got this request. It's a GET request on a specific path, and it's identical to a request that I've already seen. And last time I saw that request, the server responded with this exact response. So instead of bothering the server with this request, because they always respond with the same thing, I'm going to just respond with the response that I have cached and not bother the server with it at all. We don't want that happening. With a random key, that aggressive cacher isn't going to have that option because it's going to see a request that's not identical to any request it's ever seen before, or maybe by astronomical odds, it's identical to 1 out of billions that it's seen before. But it's not going to cache that because it's a different request, and it's going to get a different response. Every time it gets this request on this path, it's getting a different response. It's not going to cache that anymore. Because if it does cache it and says, I'm not going to bother the server, well, that defeats the whole purpose of WebSocket. We don't have a WebSocket connection anymore because the whole purpose is to get this request to the server and keep the TCP connection open. If we never even get the TCP connection to begin with, the cacher is going to respond with the response, and then the client's going to keep the connection open, but we never even got the connection. The load balancer or reverse proxy is going to close the connection, and we don't have a WebSocket connection. We defeated the whole purpose. So we want to make sure our endpoint, our end server, actually gets the request. So that's why the key's random every time. Just in case somebody tries to get a little too cute with their caching, that's going to prevent it. And then once we have this connection, we have fully duplex communication over the WebSocket connection, this TCP connection that we've upgraded to WebSockets. And once we have that, we're going to speak in WebSocket frames. Again, the details of that we're going to save till Wednesday. And we're going to start parsing in bits. I might be the only one who gets excited, but I get excited about this, that we parse in bits. So the progression of the course, we start by parsing in strings in homeworks 1 and 2. And then for homework 3, when we have multi-part requests that contain the bytes of an image or a video, we have to start thinking about bytes. We can't take our entire request and convert it into a string anymore. We have to move into byte parsing, which for Python is mostly like string parsing. You just have to make sure you never call decode. And then most of the byte parsing is very similar to string parsing. Python syntax is really nice for bytes. And then for homework 4, we have to go all the way down to the bit level. We have to actually be aware that each of those bytes is 8 separate bits, and each one of those bits might have different meaning. The reason I like it is because we learn so much about bits as computer scientists. We have 191 and 341, 220 even, quite a lot gets into the bits. We learn about it a lot, but it rarely actually comes up in our day-to-day programming. And this is one spot where it's like, hey, all that knowledge that we had to learn about binary actually comes into play. We have to learn about, we have to talk about exclusive ORs and bit masks and stuff like that. So I always do enjoy it because we actually get to use that knowledge that we were forced to learn. It actually is practically applicable to something that we're doing. That's the reason I get excited for it. But I get excited. I might be the only one, but I get excited. And this is the structure of a frame. We'll go into depth in the next lecture. But this is similar to TCP and IP in that we're assigning a meaning based on the order of the bits as they come in. So the first bit is the fin bit. The next 3 bits are the reserve bit. The next 4 bits are the opcode, etc. Bless you. And then we'll go through this and parse all of the individual bits of these frames. But we're going to save that till Wednesday. So, oh God, but yeah, some people get scared of bits, but bits, I mean, because everything, absolutely everything we do is bits. Everything is ones and zeros. But, you know, modern languages, modern software, all our tools, our IDs and everything, it gets us so far away from the actual bits that we tend to forget that sometimes. But this is one case where it's like, no. We're working with ones and zeros here. We're going to have to remember that. So it gets us back down to those roots. Okay, so in the browser, let's talk about front end a bit. The front end for WebSockets is pretty straightforward, and it's in the handout code. When you start homework 4, going into function.js, the homework will walk you through this, but go into function.js, the very first line of that file is WebSockets equals false. Change that to true, and the front end will change a little bit. There will be a third pane on the website, on the front end. And it will, more importantly, change the chat from AJAX and polling to using WebSockets. And a lot of you have seen this in the code already. It's been in there since day one, all the if WebSockets do WebSockets, else do long polling, or not long polling, polling and AJAX. But we're going to switch that to WebSockets and start using WebSockets for the chat feature. What that code does, and this is slightly different than what's in that. I think I changed the path to WebSocket or WebSockets. It's something. But what we're going to do is use this constructor. And modern browsers, by the way, do so much for us. It takes care of everything. Kind of like the file picker. You just change your input to type file, and it just does it for you. Browsers have so many features built in. It's really nice. So we're going to use this WebSocket constructor, which is built into every modern browser. WebSockets have been around long enough that we don't have to worry about compatibility unless you have some major app that you're constructing that has very old users. For example, for other reasons also, like Facebook chat still uses long polling because it's going to be compatible with every browser that speaks HTTP, which is every browser, or else it's not a web browser anymore. But anyway, we're going to use this constructor and give it a URL. The protocol is WS for WebSocket. And then I'm using this window location.host. Please do this whenever you have a situation like this. To save yourself some headaches. Window.location.host is going to get the current host name that is being used for your app. Do this instead of hard-coding localhost to save yourself some trouble. Because what some of you will do will put localhost. If you're going through a tutorial, it might have localhost instead of window.location.host. Don't put localhost here. Localhost is fine when you're testing locally. And it's going to get one of them. You're going to have one of them. It works on my laptop situations because even using Docker, which should resolve these issues and all kinds of other prevention things, it's going to work on your laptop. You go to deploy with a domain name, and your domain name is not going to be localhost, and your link won't work. So localhost is going to be your end user's device, which is not going to have your server running on it, and things are going to break. You don't want localhost hard-coded here. If you use window.location.host in your dev environment, it's localhost. When you go to deploy, it's going to be your domain name, and you never have to think about it again. You don't have to think about what your host name is going to be. Or else that's something when you go to deploy, like at the end of I guess it's just O3, Objective 3 on Project Part 2, when you go to deploy, you don't have these issues where your WebSockets don't work. Your web app will load, but your WebSockets won't work because you had this hard-coded to localhost. Some teams will still do this, even though I said this in both lectures. But make sure you do window.location.host. Save yourself some headaches later on down the road. And then finally, the path, /socket. What this is going to do is send an upgrade to WebSocket request to your server when this constructor is executed. The constructor is going to send that HTTP request to this path. So this code is going to send a request to the path, a GET request to /socket, the path to /socket. In the homework code, I think it's WebSocket. It'll send a GET request to /WebSocket. If you want to use a different path, you change this in your front end, and you'll use a different path. And that establishes the connection. And then to send and receive messages, receiving messages, we're going to use this onMessage field of the socket object that we created and set it equal to a function, and that function is going to be called with the message as an argument. So just like we did with... Is that mine? And this is going to take a function, just like we did with the router, how our add route takes a function. So I don't have to talk about first-class functions again right now in depth. But we're going to assign a function. So I don't have parentheses right now here. I'm not calling the function. I'm assigning this variable a reference to this function, which is this function here. And then the socket is going to call this function with the message every time we receive a WebSocket message. And here I'm just printing it to the screen, but this is where you would process the message. In the handout code for the homework, this is where we're parsing JSON, and then rendering that message as HTML in the chat div. And then if we want to send a message, socket.send, and then whatever we want to send to the server, that's going to send that, encode this as a WebSocket frame and send it over to the server. And that's it. That's on the front end. Everything else is what you actually want to send and what you want to do when you receive a message. But that's it for the front end. The browser handles everything else for us. So there's a very back-end heavy objective. Next week when we talk about WebRTC, it's going to be fairly front-end heavy, actually really front-end heavy on that one. But this one's really back-end heavy. Okay, let's talk about some code stuff in a few minutes. There's 2 big points I need to hit. Actually, I want this resized. So when we have a WebSocket connection, what we're going to do, let's think about what's going to have to happen. We're going to get a request. We're going to parse it. We're going to check the path. We're going to see, put it in our router or whatever. Actually, 3 points I want to make. If we're going to put it in our router and whatever, and send a response. We're going to send the response. And then we need to leave that connection open. So how do we leave the connection open is our next challenge. That's what we have to figure out what to do. And the bigger question is, how do we close the connection? Because we close the connection all the time, and I mentioned this in a few lectures, but it's going to be very important now, is we let the handle method resolve. Once we get to the end of the handle method and that stack frame's done, the socket server is going to close up that TCP connection, wrap it up, disconnect, tell the client that we disconnected and everything, and just clean everything up. So we need to not get to the end of the handle method. And one way to do that, it's a good use of a while-true loop. So we need a forever loop, enter this infinite loop, and receive our WebSocket frames. Whenever we call receive, we're going to expect that to be a WebSocket frame, and we're going to do send all whenever we need to send a WebSocket frame over that connection. So we'll get in an infinite loop after sending the response. What I recommend is to have your handle request take another parameter. I'm going to pass a reference to my handler to the handle request method, and then pass that to my function. The function that's being called by my router when I route to the WebSocket connection, that takes a reference to the handler. So inside that function, I can have my infinite loop and then access send all and receive inside that function, inside an infinite loop. And then I can use break whenever I detect that the connection was disconnected by the client. I'll use break to get out of that loop. So we're going to have an infinite loop. I don't have time to show it in the code, but I'll just give you the punchline here, is add threading here. Since we have connections that need to stay open, we need to handle multiple connections. We're going to put each connection on a separate thread, and it's super easy to do that with the TCP server. Add the word threading right here. Everybody should add the word threading right here to handle multiple connections.